All right, so in our last lesson about limits, we're going to learn about trig limits, and most importantly, something called the squeeze theorem, which is another really important theorem that could come up. So we've talked about all these different ways, like we've done algebraic manipulation, we've done, of course, direct substitution, we've talked about those tinies that you can use. This is kind of a last resort if nothing else works and you're specifically dealing with trig. So this says even if you can't find something directly, the squeeze theorem teaches you how to find an indirect, and so it works like this. Say you know something about a function g and you know something about a function h, and you also know, as you can see on this picture, our function f is always in between h and g, and so we say it gets squeezed in between h and g. So here's the way the theorem works. It says if our function f is always in between g and h for all x equals or not equal to c, remember we don't care what's happening right at x equals c. Okay, so that's how the theorem starts off. So if g is always below f and f is always below h, for everything on this interval except for c, maybe c, but we don't care about c. More importantly, there's probably going to be a hole there on at least one of the functions. And let's say we also know this is true. The limit of g as x approaches c is L, and the limit of h as x approaches c is L. So that's the second thing we know. So the second part says, as x approaches c, g is approaching a y value of L, and h is approaching a y value of L. So the way the squeeze theorem works, it says, as long as f is always between g and h, if g approaches the limit L and h approaches the limit L, since f is always in between, f has no choice but to also approach that same limit. The reason we call it the squeeze theorem, we basically say that function f gets squeezed towards that same limit of L. So even if there's a hole on our function f or something like that, you can still figure out what its behavior is going to do based on the squeeze theorem. So let's look at a couple of examples. Okay, and so the squeeze theorem has a very specific process, and so the first time I'll go through it very slowly, and then hopefully you guys will catch on quickly. So we always start with one of the following. So here are two things that we know. Okay, so we know this. We know that sine is always between 1 and -1. We can use theta just as a generic angle. And we also know the same thing for cosine. So these are just like facts that we know about sine and cosine, and we're going to use them. Okay, so here's how this one starts. We start by knowing that this is true. Sine specifically, since this one has to do with sine. And let me actually write another way. So you could also write it like this. Like if this is true, you could also write it in this kind of condensed absolute value form. So if it's saying the absolute value is less than 1, that's the same as saying it's between -1 and +1. So then same thing for this. So depending on the problem, we might need either form or the other. So when you're looking at a specific example, what you do is you look to see whether it has to do with sine or cosine, and then you pick one of these two to go off of. So we start with this. We start by knowing this inequality is true right here. All right, so that's kind of like your opening statement. And then this could be any angle at all. Doesn't matter what you've got on the inside here. And so since this sine function has 1 over x in the middle, that's totally fine. We can use 1 over x as our angle, because it works for any angle no matter what you plug into that sine function. So now we know that this is true. Okay, problem is, this is not the function that we have. Our function has an x multiplied in front. So what we can do is we can take both sides and we're going to multiply by the absolute value of x. All right, so multiply both sides by the absolute value of x. So when you multiply the left, since they're both absolute values, you can just kind of absorb it into the same absolute value. Okay, so now we know that this statement is true. Oops, I just got pen everywhere. So we know this statement is true, and now we're at least getting closer because this is exactly what our function looks like. Okay, so now, remember what happens here. This is like Algebra 1 stuff. If you've got an absolute value equation, you take this part out of the absolute value. So that's what we're going to do here. This comes out of the absolute value. And then since this is a 1, that means this 3-piece inequality gets sandwiched between 1 and -1. So that's what we can do here. Gets sandwiched between this and the negative version. Okay, so now we know that this is true. Let me show you something on the calculator. I think you guys will find this at least somewhat cool. We'll see. So on a graph page, or you can type all of these into the y equals if you have an 83 or 84. So the first one I'm going to graph is our function that we're working with. So x times the sine of 1 over x. So we've got that function. And then the next one I'm going to plot is the negative, and then absolute value comes right here next to the 9. You've got all these symbols right down here. So you can get the absolute value of x, and then the positive absolute value of x. Okay, so we've got all three of those graphed. Now, it doesn't look like much when you're looking at it right now. We need to zoom in to see what's actually happening inside here. And you'll see once we zoom in, it gets really, really cool. So menu, window zoom. We want to zoom in, the third option. So I'm going to click right in the center there and start zooming in. Okay, so you can see it a little bit there. There's a lot of wiggling happening in the middle. I'm going to keep zooming in, zoom in right on the center. Okay, so you can start to see it more. Can you see all the wiggling that's happening in between those? And I'm just going to zoom in a couple more times. Zoom in. All right, now it's getting cool. So now you can see that as you're getting closer and closer. So now, I mean, we're in really, really far. This is negative 0.66. This is positive 0.59. Let me go just one more time so it'll fill up the screen. There we go. Okay. So there are your functions. I think this is a super, super cool function. I'm sure you can tell, see how this is starting to get closer together in the middle. The more you zoom in, there are going to be even more oscillations. You can't zoom in to a point where you can't see the oscillations anymore. So let me give you a quick sketch. So you've got the negative absolute value of x, you've got the positive absolute value of x, and then depending on where you start the graph, this is just this huge looping function, and it literally just touches the edges, and then it starts to oscillate like crazy in here. It's going to look something like that, probably a little more symmetric than I actually graphed it, but it's the middle that matters. It's these crazy oscillations that happen when you get in towards the middle here. So the way the squeeze theorem works, this perfectly fits with the g of x and the h of x, and then here's our f of x in the middle. So the squeeze theorem, you would basically say this limit, the limit of the negative absolute value of x as x approaches 0, and it's only because this is what we're looking for up here, as x approaches 0. This function, you can just do direct substitution. You can plug a 0 right in there, and you get 0. And the limit of absolute value of x, positive, as x approaches 0, same thing. Direct substitution works. You can just plug it right in there. So since you know that this is true, and you know that both of these approach 0, since our function's in between, it has no choice but to get squeezed to 0 as well. Okay, so that's how the squeeze theorem works. So we're going to add in a couple more elements here. These are just important trig limits that you should have memorized. And this one we've done already. You've seen this one before at the beginning of the limits chapter, actually. So we've got that one, and then we have a second one. Okay, so there is a second function that you can go with. All right, so it looks something like, oops, I wrote this. I'm sorry. This is backwards. This should actually be 1 minus cosine x. I apologize. Okay, so let me show you that one, just so you believe me. So numerator, 1 minus cosine x, and then the denominator is x. So it's not a very exciting function, but if you were to plug in 0, you would get 0 over 0. So if you could zoom in far enough, you actually would see that there's a hole there, but you can tell that it definitely wants to approach 0. So these two are important limits that you're just going to have memorized, and we will be using them in these later problems here. Okay, so let's check out this one. This one is kind of an interesting situation here because it looks almost like this, except not quite. All right, so when we try to figure out exactly what's happening here, we're going to do something known as a substitution. So we're going to do a little change in variables. So we're going to say let theta equal 5x. Okay, and then we're going to make some substitutions. So if theta is equal to 5x, if you divide both sides by 5, you can say that x is equal to 1/5 theta. All right, so let's kind of do a little substitution here. Limit of sine, instead of 5x, we're going to sub in a theta. And then instead of x in the denominator, we're going to have 1/5 theta. So here you could say as 5x goes to 0, or I'm sorry, you could say as theta goes to 0, or as 1/5 theta goes to 0. But if 1/5 theta is going to 0, that's the same as saying theta is going to 0. So this is what we're trying to solve here. We're going to do a little bit of manipulation. So this 1/5, instead of dividing by 1/5, we can multiply by 5. Okay, and then we have this other limit property that we learned a couple lessons ago that says if you're multiplying by a constant, you can just move the constant out front and then worry about what the limit is. So move the 5 out front, and then we can do this whole limit thing in the inside here. Okay, so now the part that I have in parentheses looks exactly like this. And so we've got a 5 on the outside, and I know that limit is going to be 1. So I get 5. So here is an important little add-on to this one right here. If you have the limit as x approaches 0 of sine of, let's say, a times x, so any other constant in there, the limit is just a. Okay, so just a nice little add-on, kind of an addendum to that theorem that we've got up above. So just a secondary example there. Okay, so now the examples we're going to look at are going to use these as well as Squeeze Theorem. So these ones will directly tell you to use Squeeze Theorem. So we always start with one of the statements that we've got up above there. So we're going to start by saying that we know that this is true. We've got that. The absolute value of sine is definitely less than or equal to 1. And then we want to jump to our next step where we make this look like this. And the way that we do that is to get the denominator of x. So we are going to divide both sides by technically the absolute value of x. All right, so it's going to look like this. Really, I'm going to throw in one of these on both sides. All right, to make the left-hand side look like what I started with. So now I have this. Okay, so we're getting closer. And then finally, I rewrite this as a three-piece inequality. So this part can come out of the absolute values, and then I sandwich it in between the positive and negative version of the right side. Okay, so let's look at a graph just so you can see what we're dealing with here. And then I think you'll get the picture. Okay, so sine x over x, this is our graph. Okay, and it is always sandwiched between the negative absolute value of 1 over x and the positive absolute value. Okay, so you can see what's happening there, and now this, more importantly, make sure you're paying attention to this. This is the limit as x approaches infinity. So if you're looking around at 0, there's not much happening there, but you can see as we go out to infinity, that black line is sandwiched between the green and the pink lines. And so it goes out and out and out. So we want to see what the limit of the right-hand bound is as x approaches infinity. And as x approaches infinity, as my denominator gets bigger and bigger and bigger, this is approaching 0. And I can say the other one is doing the same. Even with the negative out front, the bigger this denominator gets, this thing overall is approaching 0. So since my upper bound function and my lower bound function both approach 0, I know by the squeeze theorem that my function will also approach 0. All right, one more squeeze theorem example. Very similar. We're going to start with my sign statement. Okay, I know that that is true, and then you want to make sure you're multiplying in whatever's missing. So since there's an x minus 1 missing, we're going to multiply in the absolute value of x minus 1 to get the left-hand side to look the way it's supposed to. So I've got this. Okay, and then to write it as a three-piece inequality, I bring this out of the absolute value. And then sandwich it between the positive version and the negative version of the right-hand side. Okay, so now we're looking for the limit as x approaches 1. As x approaches 1 here, I can just do direct substitution, plug in the 1, and I know that that is approaching 0. Same thing here, I can just directly substitute in the 1, and I know that this will approach 0. So therefore, I know that my function has to be squeezed in the middle, and it will also approach 0. Okay, so relatively straightforward once you figure out how you're supposed to do all the manipulations here. You find one above, you find one below. If they go to the same limit, then our function has no choice but to squeeze to that same limit. All right, so next, a couple that are just going to use the two examples that I gave you. So kind of tying in the algebraic manipulation with these two things that we learned right here. Okay, so this one, just a little bit of manipulation that we have to do because we know what to do with all of this, but we don't really know what to do with the 3. So we can treat it as a constant, kind of bring it out as a 1/3. So that'll look like this. Okay, so don't forget that the 1/3 is there out front. That's going to be part of your answer. And then everything else that I have here fits with this. If you've got some other constant out front, it just ends up being that constant. Just like this one just ended up being 5. So this is actually the exact same limit that we're looking at here. So this ends up being 5. And so, of course, this simplifies to 5/3. So a little bit of manipulation, kind of going along with the trig rules that we just learned. Okay, so let's try this one. This one, we can write this as limit as x approaches infinity. And then what we're going to do is try to compare it back to this, sine x over x, and we have these limit properties that have to do with powers. I'm going to pull this one back up. You guys remember this limit property? If you've got a function raised to a power, it's the same as the limit of that function raised to that power. So we know this one. This, first of all, is squared, so I'll kind of do it step by step. So it's the same as taking this and squaring it. The x is squared, the sine is squared, but this is not quite what we want. It's actually the reciprocal, and then remember we can write reciprocals as the negative first power. So this is actually the limit as x approaches 0 of sine x over x to the negative second power. So let's compare this to this. We've got the sine x over x part, except it's flipped, so our power is negative, and it's squared, so our power is a negative 2. Okay, so next the property tells me I can just take the limit and then raise the limit itself to that power. Okay, so the limit, we know from what we had written down, is going to come out to be, 1. I was thinking of the negative from this. It comes out to be 1 raised to the negative second power, which is, of course, still 1. Okay, so a little bit of manipulation there. A little bit more manipulation here. If you look at our two options, we're not going to get it to look like this because it isn't sine at all, but we can get it to look like this. We've got 1 minus cosine in this numerator, and then we have cosine minus cosine squared in this numerator, so what we can do is factor out a cosine. And then when we factor out a cosine, this is left with 1 minus, and this is still left with cosine, and then we've got the t in the denominator. So you can think of this as like cosine over 1, if it helps you make sense of this. So since we've got the product of two different things here, remember we have a separate limit property that tells you you can take the limits separately and then multiply them together. Okay, so the limit of this, and then times the limit of this. So with the limit on the left, don't try anything fancy, just do direct substitution. So if you plug in 0, the cosine of 0, if you remember your unit circle, is 1. And then here, we know that's 0 from what we had out front. Okay, so 1 times 0, of course, is going to give you 0. All right, so that is actually the end of our chapter.